So that's the title slide.
Yes.
Oh, let's see if I can go next slide. There we go. Got to go down there. All right, so I want to talk about 5 things over the course of this presentation. I want to distinguish between 3 related things: convergent plate margins, subduction zones, and arc trench systems. I'm going to define them and hopefully we can be more precise in what we talk about. And then I'm going to talk about how the upper and lower plates of these systems control the behavior of the arc trench system. Then I want to talk a little bit about how do we study subduction zones. These are deeply buried features. They're not, we can't just go out and walk and look at them. We have to come about them from a different perspective. I'm going to talk briefly about the seismogenic zone and then about arc magmas. And then I'll try and bring in some stuff about the Aegean system, which is very interesting. So next. So convergent plate margins, subduction zones, and arc trench systems. So people tend to mix these up, but let's be clear. A convergent plate margin is a 2-dimensional surficial plate boundary that is geometrically required for plate tectonic theory. It is a destructive plate boundary. It has no information about how the plate is consumed or destroyed, simply that it goes away at that plate boundary. A subduction zone is implied but not required by a convergent plate margin. It is a 3-dimensional region defined by asymmetric sinking of oceanic lithosphere in particular, not always, but in general, into the mantle. It's defined by earthquakes to depths as great as 670 kilometers, and in some cases can be traced deeper with seismic tomography. Subduction zones are not required by plate tectonic theory, although, you know, there's got to be some way to destroy a plate. And finally, the third thing is the arc trench system. This is the bathymetric and crustal expression of tectonic and magmatic processes above a subduction zone. Sometimes it's just called an island arc or a magmatic arc or just an arc. So ancient arcs and sometimes evidence of ancient subduction zones can be recognized in the geologic record. So just students, try and keep these in mind when you're talking about these things. So there's 55,000 kilometers of subduction zones and continental collision zones. A recent initiative in the United States was called geoprisms, and they focused on different areas in the Aleutians, in the Cascades of Western North America, and in Northern New Zealand. You can see you've got a nice one, little one over there. Hey, if I use my pointer, can you see it? Can you see that?
Yeah.
Okay, so I'll use it. So yeah, you're over here and you've got a nice little one over here.
Yes.
Very nice. And then collision zones are just a kind of convergent plate margin. Mm-hmm. I mean, they're quite different because we have the deepest points in the earth are in trenches and the highest points in the earth are in collisional mountains, but they're related. All right, so convergent plate margins are geometric requirements of the Euler theorem. So these are surficial features like divergent. Here's a divergent plate margin. Here's a conservative plate margin or a transform. Here's a destructive plate margin or convergent plate margin. No information about how these plates are destroyed, only that they are. And in fact, we have to have something in the 3rd dimension to do this. Oh, I should make one last point. Very important from a geologic perspective is these kinds of representations have no information about the nature of the crust, which is very important for the tectonics and the magmatism of arc trench systems. So here's a nice little cartoon with the main elements of a particular kind of convergent margin. This is an extensional convergent margin. I've done a lot of work in the Marianas, so in many ways, This is the Marianas. This is the Pacific Plate being subducted. This is the eastern part of the Philippine Sea Plate with the magmatic arc, a broad forearc, which is often ignored in reconstructions, and a back arc basin with seafloor spreading. And this is a very dynamic system, as you can see. If you just follow the isotherms, you see this doing incredible things. Like normally out in the oceanic realm, the 1,000-degree isotherm is in the lithosphere at maybe 40, 50, 60, 70 kilometers. But because this plate is dragged down, those isotherms go way down like that. And that has a huge effect on transporting volatiles into the mantle. That sinking also drives the overlying mantle wedge, which is a asthenosphere mostly, and it gets circulated with it. Those fluids come off of the subducted slab, stimulate melting in the convecting asthenosphere, and we end up with arc volcanoes. Okay, so this is a really, really dynamic system, and here I am presenting it statically, which is not the best way for anybody to understand any dynamic system. So I want to show you an 11-minute video. This is on YouTube. Just Google Plate Tectonic Basics 1. You can see it anytime. And here we go.
Plate tectonics is a theory that describes how the solid Earth operates. In this video, we will look at details of the two most important plate tectonic processes, the creation of new plates at oceanic spreading ridges and the destruction of plates in subduction zones. The Earth's outer surface is divided into a mosaic of rigid plates by a network of plate boundaries. The boundaries are the main sites of plate tectonic activities. There are three types of plate boundaries: divergent plate boundaries, where two plates move apart; convergent plate boundaries, where two plates move towards each other; and transform faults, where two plates slide past each other. Divergent plate boundaries are also called oceanic spreading centers and are where new plate material is continuously created. Convergent plate boundaries mark where one of the two converging plates sinks beneath the other plate in a subduction zone. Convergent plate boundaries are deeply submerged, and an oceanic trench marks where the downgoing plate bends down to begin its descent. We now look at what happens deep in the Earth beneath divergent and convergent boundaries. Geoscientists refer to Earth's plates as lithosphere. Lithosphere is a rigid shell of rock about 100 kilometers or 60 miles thick. It is composed of Earth's outermost compositional layers, the crust, and the uppermost mantle. Plate tectonics happens because lithosphere slides over deeper, warmer, and weaker mantle called asthenosphere. The origin of the force for this motion is the sinking of dense lithosphere in subduction zones. Let's look at lithosphere creation beneath a divergent plate boundary where new material for two plates is produced. About 50 kilometers under the oceanic spreading center, the asthenospheric mantle rises and begins to partially melt. Melting here occurs when rising hot asthenospheric mantle experiences lower and lower pressure. Melting by lowering pressure is called decompression melting. These melts, or magmas, separate from the remaining solid mantle and flow up towards the region of plate separation, concentrating beneath the ridge axis. Geoscientists refer to this as two-phase flow because two phases, one solid, the other liquid, move independently. Liquid magma flows up, while solid residual mantle flows sideways. Eventually, the magma pooled beneath the ridge axis erupts as lava. When this lava cools and solidifies, it becomes the volcanic rock known as basalt, which makes up Earth's oceanic crust. Older basaltic crust moves symmetrically to either side of the spreading axis to create space for the new crust. This is the plate tectonic process known as seafloor spreading. At the same time, under this new crust, a stenospheric mantle cools and is added to the base of the thickening lithospheric plate. The new plate slides slowly away from the ridge, and the top of the plate, which is basaltic seafloor, collects sediments that slowly sink in the ocean. Water infiltrates into the crust and incorporates itself into the structure of the crust's constituent minerals, hydrating the aging oceanic crust. Much of this hydration happens at the spreading ridges, where spectacular hydrothermal vents teeming with life are found. Sediments and hydrated oceanic crust will become important chemical players in subduction zones. As the oceanic lithosphere ages and moves away from the divergent plate boundary, it becomes colder, thicker, and denser. When oceanic lithosphere becomes denser than underlying asthenosphere, it becomes gravitationally unstable and wants to sink. Eventually, oceanic lithosphere does sink into the asthenosphere at a convergent plate boundary in a subduction zone. Plate convergence can create enormous strain at the interface between the two plates, causing powerful earthquakes in a region known as the Seismogenic Zone. As the plate sinks deeper, it drags the overriding asthenosphere down with it, inducing asthenospheric counterflow that draws in more asthenosphere. At the same time, the sediments and hydrated crust of the downgoing plate are increasingly squeezed and heated as the plate descends, releasing the water acquired over millions of years on the seafloor. The released water and sediment melts rise from the subducting plate into the overlying asthenosphere and cause it to partially melt. This type of partial melting, induced by fluid, is called flux melting. The melt produced is also basaltic magma, as in the case of the oceanic ridges. But this magma contains much more water and water-dissolved chemical elements, which distinguishes it from magmas produced at ocean-spreading centers. The buoyant basaltic magma rises towards the surface. Some reaches the surface and erupts in volcanoes, but some magma stalls and ponds in the lower crust of the overriding plate. Ponded basaltic magma heats the crust and causes it to partially melt, forming secondary granite magma. At shallower levels in the crust, ponded basaltic magma can excavate one or more magma chambers where the magma cools and fractionates, a process where mineral crystals freeze out of the liquid magma and sink to the bottom, changing the basaltic magma's composition towards granite. Basaltic and granitic magmas can mix in magma chambers to form a spectrum of intermediate magma types. Granitic magma has a low density and rises towards the surface in balloon-like masses called diapirs. Some magma diapirs stall before reaching the surface, where they cool and solidify to become plutons. Plutons can be exposed on Earth's surface where erosion cuts down into the crust. An example of exposed plutons is the granitic core of the Sierra Nevada of California. It is probable that the Earth's continents are mostly constructed of this type of material. The key plate tectonic processes just described, the upwelling of mantle beneath oceanic ridges and the sinking of cool lithosphere in subduction zones, is part of a convecting mantle system that dissipates heat from the Earth's interior. Sinking of lithosphere in subduction zones powers the plate tectonic machine and makes the plates move. These processes also regulate Earth's carbon and water cycle, are responsible for forming many ore deposits, and may be linked to the evolution of complex life. Among the planets and moons of our solar system, only Earth has plate tectonics. Perhaps there are other planets in other solar systems that have plate tectonics waiting to be discovered.
Okay, so that you can see that on YouTube. Just Google, go to YouTube and search on plate tectonic basics 1. So, all right. So these processes are responsible for creating the crust of an arc trench system. And there are 4 main elements of that, beginning with the trench. The forearc is between the trench and the magmatic arc. And it's 200 or 300 kilometers wide because the magmatic arc is typically situated at about 110 kilometers above the subducted plate. And so it takes that much lateral distance for the plate to bend to 110 kilometers. And then anything behind the main magmatic front is the back arc. So sometimes called the retro arc. Sometimes people confuse back arc with back arc basin. Not all back arcs have back arc basin seafloor spreading, but these are the 4 main elements and why they are where they are. Anybody that puts a magmatic arc up near the trench just is not understanding the geometry of a convergent margin in an arc trench system. All right, so there's a few things we want to talk about. I have trouble with numbering there. There's the importance of the overlying plate. There's the importance of the subducting plate. And there's big differences between arc trench systems around the Pacific. Here in the Eastern Pacific, if you're going to study arc volcanoes, you'd better be a mountaineer that can deal with cold weather. And if you want to study the ones in the Western Pacific, a lot of them require that you have the ability to swim like a fish or have technology that can help you do that. So the overriding plate exerts strong controls on the nature of the arc trench system. So ATS for short, arc trench system. An arc built on continental crust, the magma supply, basaltic magma from the mantle wedge has to interact extensively with the crust and remelts. So you get mostly felsic magmas. These are also areas with high sediment flux. So you're likely to get a forearc basin and an accretionary prism where the sediments get scraped off of the downgoing plate. In contrast, oceanic ATS systems on oceanic crust, only the tops of the tallest volcanoes are above sea level. The crust is thicker. You tend to have more mafic magmas. You have a low sediment flux, thin sedimentary cover, and often no accretionary prism. Instead, tectonic erosion dominates the forearc region. Okay, so the Andean type arcs have volcanoes that rise high above sea level. So I can't even pronounce this volcano, but that's higher than any mountain in the United States. And then these are very nice places to put observatories. So especially the extinct volcanoes, because you can get so high up and see through the clear sky. That same volcano you can see off in the distance there on the right. On the other hand, in oceanic arcs, these are often submarine. This is one we studied. It's in the Marianas called Northwest Rota 1. The summit is about 500 meters below sea level. Started erupting sometime before 2003, quit erupting sometime between 2010 and 2014. This is the eruption that we watched. And this yellow is from sulfur. Sulfur, SO2 comes out of the vent and recombines with water and disproportionates into elemental sulfur, which is the yellow, and sulfuric acid, which lowers the pH around this down to a pH of 1 or so. So a lot of ways that people want to study these is with the deep sea drilling ship. show these resolution. So in 2014, we had a expedition that drilled here in the Arc, forearc, in the rear arc, and then some of the older crust in here. It was largely to understand subduction initiation, which is another one of my favorite topics. Now, the importance of the subducting plate, this is because of its buoyancy. So Ueda and Kanamori 40 years ago talked about Chilean type versus Mariana type. These were arcs under compression, or arc trench systems under compression, and these are arc trench systems under extension. And it's a reflection of the buoyancy of the incoming lithosphere. Here in the Eastern Pacific, you've got very young lithosphere, very warm, very buoyant. It resists subduction. You get crustal melts, atakites in here. You get a flatter subduction zone, a shallower trench. In the Marianas, where you have, in the Western Pacific, you're subducting old, thick, cold, dense lithosphere. You have a deep trench. You have a strongly extensional regime. The slab is too cold to melt. Instead, it's the asthenosphere mantle wedge that melts due to fluxing. And you get different types of earthquakes. Stronger compressional earthquakes in the Chilean type, no great compressional earthquakes in the Mariana type. So now this is subducting oceanic lithosphere. If we bring in continental lithosphere, which is even more buoyant, then we have a third type, which is called the continental collision zone. And that's what's happening in Eastern Turkey now. So we can think about these different densities. It's the density of the lithosphere that's important, not just the crust. So here we have 4 types of lithosphere: continental lithosphere, young oceanic lithosphere, old oceanic lithosphere, and an oceanic plateau. And so we just plug in reasonable values here. Oceanic crust, 2.9 grams per cc, continental crust, 2.7, mantle lithosphere, 3.3, mantle asthenosphere, 3.25. And you just simply compare the density of these columns and you get a first idea of how that subduction zone should behave. If you subduct continental lithosphere, which is much more buoyant than mantle asthenosphere, it's going to resist subduction. In contrast, if you subduct old oceanic lithosphere, which is denser than mantle asthenosphere, it subducts easily. Oceanic plateaus cause some problems, and young oceanic lithosphere, as we just discussed. So it's a very simple-minded way to think about the geodynamics of convergent margins, focusing on first the nature of the overriding crust, and just as importantly, the nature of the subducting lithosphere. So here we have the situation in Anatolia. Here we have you're subducting, or you've tried to subduct very buoyant continental lithosphere. It's not subducting. In fact, it's colliding. And as a result, Anatolia has to get out of the way. Fortunately, there's another subduction zone over here that's willing to take Anatolia. We'll talk a little bit about that. This one is subducting dense old lithosphere. I mean, some people have even argued there's Permian oceanic lithosphere in the Eastern Mediterranean. I don't know if that's true or not, but clearly the behavior of the Aegean convergent margin is telling you about very dense oceanic lithosphere being subducted now. Now, here we can see why the Eastern and Western Pacific arcs convergent margins behave so differently. In the Eastern Pacific, against South America, you're subducting very young oceanic lithosphere. It's quite buoyant. In fact, you've entirely subducted the ridge up here off of California. Whereas in the Western Pacific, you're subducting some of the oldest oceanic lithosphere that we know about, early Cretaceous and Jurassic. So it's no surprise that we have a Mariana type convergent margin here and an Andean type here, just from seeing that map of oceanic crustal age and inferred buoyancies. All right, so If we subduct young buoyant seafloor and young buoyant anything, continental crust, this will result in overall compression, and it will form a rear arc fold and thrust belt. So here we have the rear arc of the Andes, Chilean type subduction zone, and here are some cross sections. So here is the Pacific plate coming in. Actually, that's the Nazca plate. Here is the Andes in here. And then in the back arc, you have a compressional regime. Oil companies are looking for hydrocarbons there. Some quite well worked out structures. Fold and thrust belt, classic thing that any structural geologist would be happy to study. It's not a collision in the sense we use continental collision, but it's a thrust regime. And this is all in the back arc. In contrast, in these extensional systems, especially in the Marianas, the back arc regime is strongly extensional to the point of seafloor spreading. This is called the Mariana Trough. It's quite confusing because the deepest part in the ocean is the Mariana Trench. So they sound very similar, but in fact, the Mariana Trough is seafloor spreading. The Mariana Trench is the convergent plate margin. So we're seeing that here. We're here in this wonderful little microcosm. We have the subduction of buoyant lithosphere causing all of the problems that we see in continental collision zones. And over here, we have a Western Pacific-like back arc basin extensional regime. And Turkey is sitting right in this transition from collision to back arc extension. Ah, I got to show you this one. We made this. Some of you might have seen that already, but we made a video. One of the things we like to do here is make videos. I have to escape, copy. I think I have to stop sharing, right? Is that right? Or can I just put it in there?
I think you need to stop sharing. Yeah.
Okay, stop sharing. And then I'll reshare. So we like to make videos, and the earthquake you guys had a month ago or so was really interesting.
Along the fault and an earthquake.
Oops, I got to start it over. Can you see that?
Associated with this earthquake trends
So
east
you
west.
share the YouTube screen again.
South.
Yes.
So you haven't shared the YouTube.
Oh, I haven't. Okay, hang on. Oops. Let me go to sharing. Where is sharing? There we go. I have to click that. Now do you see it? Failed to start. Please try again. Share. Share. Oops. So I need to get out of here. Escape. Go back to sharing. Share. Now do you see that?
Yes.
Yes.
Okay, good. I'll go full screen.
Hi, I'm Allie Sealander with UTD News, and today we're going to talk about what caused a large earthquake that recently shook Greece and Turkey. On October 30th, 2020, a magnitude 7.0 earthquake struck Samos Island, Greece, just off the shore of Turkey. This devastating quake caused over 1,000 injuries, and unfortunately has so far resulted in at least 115 deaths, marking it as the deadliest earthquake of 2020. A resulting tsunami reached many coastal cities, including the beautiful city of Izmir, which unfortunately was especially hard hit, with over 20 buildings destroyed. This region is very seismically active. Over the last 70 years, it has seen 36 earthquakes with a magnitude of 6.5 or greater. The earthquake occurred 21 kilometers beneath the surface and was caused by rupture and movement on a normal fault. This is a type of fault where the rock above the fault plane moves downward relative to the rock below it. The fault movement is caused by extension or stretching of the rocks to the point of producing motion along the fault and an earthquake. The fault associated with this earthquake trends east-west, which means that extension is happening in a north-south orientation. But what is causing this extension, and why do we have all this faulting and seismicity in the area? To get to the bottom of this, we need to delve into the plate tectonics of this region. The Samos earthquake occurred within the Anatolian Microplate, which is crammed between three other plates. To the north is the massive Eurasian plate, to the southeast is the Arabian plate, and to the south is the African plate. The Arabian plate is colliding with Anatolia, squeezing it against the Eurasian plate, so that Turkey has to escape to the west. Meanwhile, the African plate moves northward and sinks beneath the convergent plate margin. Here, the African plate subducts or sinks beneath the southwestern Anatolian microplate in a subduction zone. As a result of continental collision in the east and subduction in the west, the Anatolian microplate is very dynamic. This tectonic activity can be visualized using GPS, tracking how different parts of the Anatolian plate move in response to these different forces. What we can see is that the Anatolian plate is essentially making a plate tectonic U-turn. In eastern Turkey, the Anatolian microplate is moving slowly west-northwest away from the colliding Arabian plate. In central Turkey, it moves more rapidly westward. And in the west, the Anatolian plate beneath the Aegean Sea is moving very rapidly south. These movements are accompanied by a lot of deformation and faulting, which cause a lot of earthquakes all over the Anatolian plate. It was one of these faults, right in the center of the Anatolian plate, that slipped and caused this devastating timber. That explains the faults, but what about the stretching that caused the faults to rupture? The answer is found in the convergent plate boundary, about 350 miles south of where the earthquake occurred. The northern part of the African plate that is subducting beneath the Aegean Sea is very dense. In fact, it's so dense that as it is subducting, it basically falls back on itself. The subducting crust collapses and rolls backward to the south as it sinks. And even though the African plate moves slowly northwards towards Eurasia, the sinking and rollback of its dense crust is faster than the plate's movement, causing the subduction zone to retreat southward. Basically, for every one step forward, the African plate in this region is taking 2 steps back. And like a friend falling into a pool, the African plate pulls the Anatolian plate with it, stretching it along the way. It's this pulling to the south that is causing the stretching or extension several hundred miles north of the convergent plate boundary. As you can see, the Anatolian microplate is very active, and more earthquakes can be expected in and around the area in the future. Thanks for watching, and don't forget to subscribe to catch more episodes of Geo News. See you next time.
Okay, so that, am I back? Yeah, stop. So we have a YouTube channel called UTD Geoscience Studios. So all you have to do is go there, see what we've got. But that was a really interesting earthquake. So let's go back to the lecture. But let's go to share. I got to go to share. Share. There we go. Share there. Share. Okay, you see my PowerPoint again?
Yes.
I'm getting good at this. All right, so how do we study subduction zones? So there's lots of tools and there's lots of specialties. And one of the challenges is to get these communities talking to each other. So we can start in the near the trench. You know, geodesy, especially global GPS, is a very important way to study what's going on at the plate interface and in the back. Igneous rock compositions and magmatic volatiles that are contained in phenocrysts are very useful. Geophysics is very important for locating earthquakes, understanding the structure of the subducted slab, And at greater depths, mantle tomography is useful for tracing the deeper continuation of the slab beyond where the seismic imagery is, and seeing regions where the mantle is slow and probably partially melted. So in addition, we need things like numerical geodynamic modeling. We need studies of exhumed ancient subduction zones, blue schists, eclogites, and experimental petrology. So we can't really make advances in our understanding of subduction zones without a wide range of geoscientific investigations. And there'll be more in the future. And in addition, we've got this problem between marine geologists and land geologists, and they tend to have different communities. But in fact, you've got to consider both things, right? In the case of Turkey, you've got to think about what's going on in Turkey, on the islands, and in the Aegean Sea, and for that matter, beneath the Aegean Sea. All right, so here we can see the subduction zone as illuminated by earthquakes. So sometimes we use the term the Wadati-Benioff zone. So these are named after two scientists who independently discovered the dipping nature of these deep earthquakes. The thing they noticed, seismologists, was that, you know, earthquakes in the earth are mostly occur in the upper 20, 30 kilometers, except in these regions where they go down to 600 or so. And that's a fundamental problem. Why are these deep earthquakes only occurring in one place? And this was recognized. Wadati did his work in the 1930s, Benioff in the 1940s. But once we had plate tectonics and knew something about subduction zones, this deep seismicity made sense. And what's happening is these subducted slabs are cold. It's the cold things that that are brittle and can break to make earthquakes, whereas hot things bend and flow and have no earthquakes. So these earthquakes are telling us where the earth is cold and brittle in deep subduction zones. These earthquakes have different causes. The shallow earthquakes, the intermediate earthquakes, and the deep earthquakes all have different causes, but all of them can be, number one, identified, and number two, provide energy to illuminate what's going on above them. So here we can see where, just looking from the distribution of earthquakes, not even their depth or their inclination, where the subduction zone is, and that's where all of these earthquakes are. And you can see there's a real big change in this margin on the southern Anatolian plate between the southwest, which is a very active subduction zone, and farther east, and even the collision zone, where much less seismic activity. All right, so with this energy that's being put in from the Wadati-Benioff zone earthquakes, we've got the geophysicists can have what they need to illuminate this area and start to get fine levels of detail with these different phases, which I can't, they're all P-wave phases, but that's about as much as I know about them. You'll have to talk to your favorite geophysicist to get more explanation. But you can see how this clever community is using the high energy that's coming out of these to understand the structure of what lies above it. And then of course, the teleseismic events, you know, these come from the other side of the planet, and these are the biggest earthquakes on the planet, so they are the source of these teleseismic events. All right, so this is, you've all seen these tomography images. What I want to draw your attention to is not the colors, red and blue, which of course means slow and fast. I want you to see the scale of the differences. This is 12% difference in velocity at a given position. So this is all referenced relative to the ambient. So this region is 6% slower than this region. This region is 6% faster. Those are amazing differences. The tomographic images, you know, show you clearly the subduction zone, and the earthquakes show it even farther. So You know, here we've got the arc volcanoes of Tonga, and you know, you can see this slow region almost certainly where the melts are being generated. You can see here the subducted slab is cold. It doesn't melt. In this case, this is a Western Pacific subduction zone. If it was melted, it would be red, but it doesn't. And it's one of the important arguments why we think the melting beneath arcs happens in the mantle wedge above the subducted slab, not in the slab, for the most part. All right, so we can also do a seismic experiment here in the Marianas. There's the trench. There's the island arcs. There's your 200, 300 kilometer forearc. And here's the back arc basin, the Mariana Trough here in the Western Pacific. And here with seismic tomography and earthquakes, we can see what's going on underneath the back arc basin. Once again, we have this very cold slab with a tremendous range in seismic velocities. This one is 20% difference. And underneath the spreading center, blown up here, we can see the slow regions associated with melting. Now, what these crosses are is where petrologists have calculated the depths of melt generation for these basaltic rocks. You know, beneath the back arc basin, it's very shallow, as you see in beneath mid-ocean ridges, and beneath the arc, it's a little bit deeper, but still not anywhere close to the depth of the slab. So petrologists, geologists, geochemists, working with geophysicists, this is a great way to make advances. And of course, the problem is to communicate between those two communities, each of which has its own terminology and expertises. All right, now let's talk a little bit about the seismogenic zone, which is this subduction interface that's shallow. So it's only 20 to 50 kilometers deep, but it's of particular interest because this is where the big, powerful, damaging earthquakes happen. There's earthquakes all the way down the slab, down to 670 kilometers, but an earthquake at 670 kilometers isn't going to bother anybody on the surface. One here will, because these are very powerful. They are very close to the surface, and they often happen either underwater, where they can generate tsunamis, or they happen under coastal regions where a lot of people live. So the seismogenic zone is really shallow. You know, this is only 30 kilometers, and the seismogenic zone is on the order of, you know, people argue 20 to 40, 30 to 50, 10, you know, but it's not deep. We're not anywhere close to the depth this slab needs to be to have an overlying arc volcano. This is out in the outer forearc, out beneath the accretionary prism. These are the 13 biggest earthquakes that have happened. 12 of them are instrumented since about 1900. One of them is inferred from geology in 1700. This is the one that makes US geoscientists very nervous. This is underneath Oregon and Washington, which is, a lot of people live there on the coast. But all of these big earthquakes happened in the seismogenic zone. So all of these in the Aleutians, these around Japan, offshore. Here we have Chile. And these are magnitude 8.5 to magnitude 9.5. That Izmir earthquake was a magnitude 7. It was a bad earthquake, but we can be very grateful it wasn't a magnitude 9. These are monster quakes. We've seen 2 of them in Sumatra in 2004 and Northeast Japan in 2011. And this is what happens. So you basically have locking between the downgoing plate and the overriding plate. And you have the earthquake cycle. This can take, you know, the plates are locked. And so the strain of the continuously moving downgoing plate is transmitted to the locked upper plate, which responds by shortening and uplifting. So that strain will build up until it exceeds the strength of the fault. This locked zone breaks, the upper plate relaxes, you have subsidence, you have extension, and this is, if it happens underneath the ocean, will cause a tsunami, and then it starts again. So with GPS, we can monitor these things and say, okay, in the Northwest Pacific, we expect these kinds of events every 200 years or 300 years or whatever. Japan's got an even better record because they've known about these tsunamis all through a few thousand years of history. That's what happens. So this was what happened offshore Northeast Japan. Normally we show the epicenter of earthquake as a dot, but a magnitude 9 earthquake cannot be approximated by a dot. This requires a rupture area of huge size. And in fact, the magnitude of an earthquake is very sensitive to the area that ruptures. This is the size of the rupture, hundreds of kilometers long, more than 100 kilometers wide. And that, when you have that much rupture, you're going to have a monster earthquake. Out beneath the ocean, facing coastal cities, and the tsunamis were terrible. So this is the area of some detail here. And with marine geophysics, reflection geophysics, the Japanese have done imaging in the same area. And there's enough, usually you don't get the resolution before and after to say much, but this was so much movement. These were on the order of 50 meters of movement that they were able to see the new faults that formed in these images. So it's a terrible event, but it's something like that that makes enough change that modern geophysical techniques can detect it. All right, let's get quickly igneous. So mantles of silicate planets will generate basalt. So we know that. We've got Mercury, we know has got an iron-free basalt from orbital images. Venus has lots and lots of basalt. Earth has too much basalt. There's basalt on the moon, old basalt, and then Mars has the biggest basalt volcano in the solar system. And then the second largest asteroid, Vesta 4, with a kilometer of 5,500 kilometers, and also lots of basalt. Basalt's very similar. It's what silicate mantles generate. 50 weight% silica, 10 weight% calcium, oxide 15%, aluminum, the rest is mostly magnesium and iron. Very simple stuff. Now, basalts are produced on Earth at 3 main places, and to a first look, they look very similar in terms of composition. But when you look at their water contents, and the water contents are determined by looking at small glass inclusions in olivines, you see that mid-ocean ridge basalts are very dry. All of them have less than 1 weight% water in these inclusions, mostly much less than 1%. Your hotspot basalts like Hawaii have a bit more, but not much more. But these arc basalts have up to 7 weight% water dissolved in the magmas that are trapped in these olivines. That's a huge amount of water, and it's one of the regions that arc magmas behave so much differently than these other kinds of basalts. They come from a very hydrous source, and it's completely expected given how these are generated. So let's think about what happens to the subducted plate. So I want to look at, this is the subducted plate. So we're subducting something on the order of 100 kilometers thick, and it's mostly mantle lithosphere. That provides most of the density needed to drive subduction. Above it is maybe 5 or 6 kilometers of oceanic crust. That creates most of the water that is released from the subducted plate to cause mantle melting. And then the top is just a few hundred meters of sediments. And sediments provide most of the trace elements that make arc magmas distinctive. So this is, sort of how we look at it, with the oceanic crust and the sediments on top. So all of these play a big role, but most of what's going down plays a much lesser role other than driving the whole system. Okay, so these fluids are coming out of that mixture and rising up into this convecting asthenosphere and being added to it, water in particular, also trace elements from sediments. And these things happen very characteristically at a given depth above the subducted slab. So this is a compilation of H, which is the distance from the surface down to the subducted slab underneath the arc volcano, the main arc volcano, the magmatic front. And what you see is this region is where the asthenosphere makes its U-turn. So it's being dragged down, so new stuff has to come in. And so this seems to be the effective terminating radius of mantle asthenosphere. Out here in the forearc, the asthenosphere can't penetrate, so this freezes out. It's incapable of melting except very early in the evolution of a subduction zone. And a stable subduction zone will localize its region of melting at this height because that's how much distance the asthenosphere needs to make that turn and constantly replenish hot material, right? So that's why we typically say this distance is typically 100 kilometers, but it can be as little as 50 and as much as 200. So how does this material contribute to the generation of arc magmas? Let's concentrate on the part that's actually providing water and trace elements, not the mantle lithosphere. And what we see here is the Central American system, Pacific Cocos plate coming in, seismicity telling us about where the subducted plate is, the forearc and the volcanic front. This is the cold nose. It's mantle material that can't be replenished because of the circulating asthenosphere. So there's plenty of fluids coming up here, but they have no effect in melting, cause serpentinization in here. These fluids, because they're interacting with hot asthenosphere, they can cause melting at the region of hottest material, which is at the core of this U-turn. And then the mantle melts. Some basalts come up without much interaction with the crust. Others interact with the crust. You get some crustal melting shown here by the location of some earthquakes. All right, so what's happening to the slab is the slab is getting heated up. This cold nose doesn't heat up this slab much, but once that circulating asthenosphere comes into contact with it, it heats up fast. And so numerical models for slabs, this is a little confusing. So we're going to talk about two subducting slabs. One is young and hot, Eastern Pacific in dashed lines. The other is old and cold. Those are solid lines. And we're going to look at three different places. So the moho, at the base of the moho, the top of the oceanic crust in green, and the top of the sediments in red. You can see this surface is really strongly affected when it's in contact with circulating asthenosphere. And that's what this step is. This is where the downgoing plate, in this case, the old plate, is moving against the cold nose, so it stays cold. And then it jumps in temperature as it starts to feel the asthenosphere next to it. Both of these jumps happen at about the same depth. So once this top of crust and sediments heats up, the it's going to be cooked, and the fluids are going to come off massively. And there is this relationship between fluid output of the subducted slab and this region of acenospheric circulation. And basically what happens is when that surface subducted sediments and oceanic crust comes in contact with that hot aceanosphere, it's like putting blowtorch onto popcorn kernels. So you can consider popcorn kernels as the subducted slab, and the popped corns slab derives fluids, and the blowtorch is the aceanosphere. So you might want to try that this evening. Not with a blowtorch, maybe just use your stove. All right, so we can see some of these things with seismicity. So, you know, Japan is beautifully instrumented with a wonderful subduction zone, or a terrible subduction zone, your choice. And these are receiver function seismic reflectivities beneath Northeast Japan. These are volcanoes, the magmatic front, and you see these very striking changes in velocity. Here it's fast, here it's slow, here it's fast again. So this is the way that Kawakatsu et al. Interpreted. This is the oceanic moho. This is the top of the oceanic crust. And this is the bottom of an overlying serpentine layer. So there's a reaction zone above the subducted plate. And these kinds of approaches are going to get more and more sophisticated as the geophysical techniques improve and as seismic networks improve as well. Very exciting. So if we think about what's happening here, let's just think about what's happening. This is the subduction interface, say about here. And this is 10 kilometers above that interface in the mantle wedge. This is 10 kilometers below that interface in the subducted plate. So down here, you know, 10 kilometers below the subduction interface, things are pretty cold. You know, that takes a long time to conduct heat from that there. And up here, where the circulating asthenosphere is, things are pretty hot. So 20 kilometers, and you have a thermal gradient of 800 degrees centigrade. So that's going to cause some incredible reaction. So we imagine that the temperature of the subducted slab interface, right there where the sediments are, is on the order of 800 or 1,000 degrees, just, you know, simple math between these end members. And above that, you'll have peridotite that's metasomatized by these slab-derived fluids. And there's this transition between this metasomatized zone just above the subducted plate and the uncirculating asthenosphere above it. So this is a very dynamic region that we're just beginning to understand. So we get very interesting metamorphisms in here. We have, you know, the incoming seafloor is metamorphosed to greenstones with, you know, and it sort of contains about 5 to 8% water, and it persists to maybe 20 kilometers deep in the oceanic crust subduction zone. And then this is converted into blue schist, which is a very distinctive rock, contains about 2% water, and exists between about 20 and 60 kilometers deep. And then finally, we have eclogite, composed of the two minerals of sodium pyroxene and garnet. And this happens maybe about 60 kilometers deep with 0% water. So this is a dewatering process from the incoming altered basalt to eclogite. So there's an entire study of like how are fluids moving through this system. And this is a very complicated diagram that was done by Kimura and Nakajima. Oops. But, you know, they're trying to show, okay, how much water is coming in this subducted plate, and then where is that water coming out? And you can do thermodynamics to tell you what the stabilities are, and from that calculate the water that has to be released. You can do mass balance on the water that's coming out in volcanoes, and you go, okay, let's see. Looks like 13 tons of magmatic water per year per meter of arc, but coming in is about 34 tons per year per meter. Even a geologist can see that there's a problem, and increasingly people are thinking that the bulk of the water is being carried deeper into the mantle and coming out either in back arc volcanoes or is being stored in the transition zone. People are.
Why did you say that geologists will have a problem with this?
Oh, because we're not good with math.
Yeah, that's a lot of, like 1/3 of the water is completely expelled. It's gone.
Yeah, I mean, this system is, I mean, one of the arguments we want to understand is how efficient is this system at removing water from the subducted slab. If it's very inefficient, then we have a problem because we still have oceans. And if it's very efficient, then we have no problem, right? If you're removing this much water every year, I mean, multiplied by the number of meters in convergent margins, then you're going to see sea level drop because it's being transferred into the mantle. But I'm not going to go in great detail here. All right, so this is another way of looking at the structure of the convergent margin. This is more from a metamorphic petrologist point of view beneath Northeast Japan. So blue schist, epidote eclogite, amphibole eclogite, you know, partial melting, serpentinite in the mantle lithosphere, their stability zones, water coming out everywhere, getting involved in the overriding plate. And this is the depth of supercritical fluid. This is another problem we have, is we have very poor understanding of the behavior of supercritical fluids. And they're gonna be the dominant fluid below about 100 kilometers. You know, that's going to be 21st century research to figure out, you know, what is the role of supercritical fluids in these systems. All right, so let's talk very briefly about igneous rocks. This is a very simple sodium alkalized versus silica diagram. These are what the IUGS recommends to distinguish between different kinds of volcanics. And we can see that mid-ocean ridge basalts are pretty boring, basalt basically. Hotspots are also pretty boring, but arcs have this incredible range in compositions, only matched by continental rifts that go from everything from basalts to rhyolites or their plutonic equivalents granite. So it's a much more interesting range of igneous rocks in arcs and continental rifts than in mid-ocean ridge basalts and hotspots. Now, there's a very interesting issue of elements. One of my favorite geoscientific journals, very cheap. Students should apply to it. You join the Geochemical Society and you get it automatically. And they did a special issue on the South Aegean volcanic arc, which is this system here. It's the magmatic arc of the Aegean convergent margin, and not too far from where you guys are. And there's some really interesting things happening here. This entire system is extending. The arc is also bowing out, and you get very strong differences in melting, with Santorini apparently having the largest amount of melting, and these volcanoes to the northwest and southeast seeing much less. So that we talked about these kinds of convergent plate margins, the Andean and the intraoceanic archetypes. And these systems have multiple opportunities to evolve in the crust. They are, you know, the basaltic, hydrous basaltic melta comes out of the asthenosphere, and establish as a magmatic system that evolves, because at a mid-ocean ridge, the magmatic system doesn't evolve. It keeps being added to the plate and moving away. But here, because these magmatic systems are continuously built above the slab at about 100 kilometers depth, the pulses of magma keep coming through this crust and interacting with it. And the interactions are not just silicate fractionation and assimilation, it's also magmatic degassing. Carbon dioxide degasses deeper than water. These fluids will play a role in metallogenesis. These, a lot of sulfur species, which are so important in ore formation, are related, respond to these changes in CO2 and water. And then if, on top, that's all we get to see is the arc volcano. We have to wait for erosion to bring these deeper levels up to us. So we've got this need for the volcanologists who are working on active systems, and of course can only see this, to talk with the people working on fossil systems, plutons, dikes, and things like that, and try and put a system together. All right, so I just want to conclude. Convergent plate margins, subduction zones, and arc trench systems are related but different. It's the sinking of oceanic lithosphere and subduction zones that is responsible for plate tectonics. It's also the main driver of mantle convection, the sinking of lithosphere and oceanic in subduction zones. Unusually hydrous magmas are generated above subduction zones, and many earthquakes are associated with subduction zones. The most powerful and dangerous ones are the shallow ones. The style of subduction depends on the buoyancy of subducted lithosphere. With upper plate extension, if you have very dense lower plate, and upper plate compression if you have buoyant. I didn't finish that, sorry. Subduction zones fail when very, very buoyant lithosphere enters subduction zones. That's collision. If there is no subduction of very buoyant lithosphere, subduction zones will continue forever. And I want to make the point that the Anatolian Aegean plate is one of the best places in the world to study convergent margins, subduction zones, and arc trench systems. Now it gets political because Greece controls the western part, Turkey controls the eastern part. But I think the future belongs to these two groups working together to understand this incredible convergent margin. And I think that could be done with European, in particular, cooperation. It is going to require some leadership from Turkey and Greece, but I think once those communities start to talk to each other about this area of common interest, common hazard, common resource, that the European community will become attracted right away. So I encourage those of you who are young and energetic and fearless to think about ways of talking about the Western Aegean plate with Greek geoscientists. And with that, I'm happy to answer any questions.